we are shooting, we'll get to it after the break, we are shooting to prove something very interesting about what happens. So we said that if you have a prime divisor above, then there is a unique prime divisor below it, assuming it's algebraic. But this is not how it works. What you really want is you start here and you want to understand this and you understand that. So you want to actually, given a prime divisor here, figure out who are those prime divisors that lies above it. Because we know that every prime divisor lies above some prime divisor below, but the search will be in the opposite direction. We are going to look at prime divisors here. Maybe this is the rational function field. We understand the prime divisors there. And we want to figure out who are the prime divisors in the next floor. And that's what we're going to do now. To understand to some extent what these are, how many are there, what's the relation between them, what are the E's and the F's, so you will see. But the first lemma for that is the following. It looks like a technical lemma, but actually it's a very important lemma. It tells you the following. It says that, even in one function field, not in extensions. So if E over K is a function field, and P is a prime divisor of E over K, because that's the only thing we have, then what I'm claiming is that there exists an X, which is E, but not in K. So that's not this one. That's not in K. And an integer K, which is at least 1, it's important that it won't be 0. At least 1, such that the pole divisor, okay, here I don't need this, but the pole divisor is exactly K times P. So what's written here? So what you should have in mind is the following. You have a function field, and you want to understand a prime divisor. Like that's geometry. Prime divisor in my mind should be a point on the curve, which we never talk about, but that's geometry. And you want to understand it. In what sense? Soon we would want to understand what are the points or prime divisors above it. And I don't know if you noticed, but we don't do geometry, we do algebra. So we need an algebraic way of understanding that P. So what I'm saying is that there is always a function which is non-constant, and the only poles of that function are in P. I don't know how many poles it will have there. I can't really control that. But there will be at least one pole, and there will be no other poles anywhere else. So in a sense, understanding now this function, or more precisely its poles, will enable you to understand P, because P is encoded in the poles. There is no plus Q. See, so that's kind of a way of encoding a point using a function. It's like you want to understand point 0, you look at 1 over x. Like the poles of this, it has only poles at 0.
But there is not for every K.
That's true. I can't choose a K, right? I mean,
you can understand it up to K.
Right. When K is large enough, I can, but because of Riemann Roch really or something. But when small K, I can't make sure that it will be just a P. Maybe it has to be like 4G times P or something. But the only thing I will care you'll see is that there is no other pole here. Yes, exactly.
An example in the rational function when
no, right. So that's a great question. For the rational function field, because the genus is 0, K is can always be taken to be 1. So so for an example, I have to go at least to like an elliptic curve or something, to something with genus 1 or higher. And we'll see today examples. I'm not sure maybe we can cook up and maybe we can revisit this lemma and figure out an example just for that lemma from the examples that we'll see. So let's prove this. By the way, the proof is one line from the strong approximation theorem, if you saw the video. Because the strong approximation theorem, it's kind of, it uses Riemann Roch, and Riemann Roch was deep, like Adels, differential stuff. And here there is nothing talking about Adels, differentials, or anything. It's a very trivial, like, in terms of what it talks about, it's just like pole divisors. It's like maybe 4 weeks ago or something. But nonetheless, to prove it, you can either use the strong approximation theorem, which just immediately gets that. If you know what that theorem is, I put a video on that. Then it means that you can choose where the poles of a function are, and you can also choose other places, and you want in those places the function to be close to some functions, but I'm not even doing that. And then this readily follows by that by taking the empty set to be the set of points you care about, and the P to be the dummy garbage point that you throw all the poles at, and that's it. But for fun, let's prove it using just Riemann's theorem, not even Riemann-Roch. Riemann's theorem was easy. It was before Adels and differentials. And it feels correct that a lemma whose statement doesn't require those things, the proof won't require those things either, hopefully. And actually it doesn't. So let's just prove it in 2 lines using Riemann's theorem and not Riemann-Roch. But again, it follows immediately from the strong approximation, which is not immediate, but almost immediate from Riemann-Roch. Anyhow, so let's see. And after that, we take the break. So let's say the G is the genus, always, of the function field. So by Riemann's theorem, just Riemann's, not Riemann-Roch, we know that for n sufficiently large, you'll see in a second what it is. It's not a mystery. So you know that always that by Riemann's theorem, the dimension is at least the degree plus 1 minus g. Right, that's Riemann. Like Riemann, that's the kind of the definition of the genus using Riemann's theorem, right? The dimension cannot lag too much behind the degree. And we know, so, okay, so what's the degree of np? It's at least n. I mean, it's n times the degree of p, and p could have like higher degree, but it's at least n. And I want this to be larger or equal than 2. I want to choose n such as this holds. That's for sufficiently large n, that's what I really mean. I want n to be larger than g plus 1. Larger or equal than g plus 1. But algebraic people are proud by not specifying the constants, like for large enough. And if you want, you can do the math. It's actually kind of surprising how amazing algebraic people can do the math, like the arithmetic of moving like plus 1 correctly. Because they believe in structure, they don't believe in computation. It's almost inherent to their culture. Like, don't compute, understand the structure, right? That's what they do. And remarkably, it works. The degree of, no, it is at least 1, the degree of p. But then this means that this is at least n. Yeah, because the degree is always, it's like right, it's the extension of the residue field over k. It's always at least 1, and it could be higher. If it's higher, it's better for us. Good. So I want this to be 2. Why do I want this to be 2? Usually, you want this to be 1. But why I want it to be 2? So what I'm saying is that this means that there is some x in E, which is not in K. I mean, starts to look good. Such that xe plus np, like this divisor, the principal divisor of x plus that is at least 0. Why? What does this line have to do with this thing? Exactly, because this means that the dimension of this Riemann-Roch space is at least 2, because that's what's written there. And if it were 1, it's already nice. It has something there. But when it's 1, it's isomorphic to k, because k is always in the Riemann-Roch space. So when it's 2, then there is something that's not just in k. So because it's at least 2, there is some x which is en not in k in this Riemann-Roch space, and explicitly it means that. Very good, yes. So see, it's a little bit kind of tricky, but we're trying to prove that from Riemann's theorem. So it's fair that we'll work hard. 1, yeah. But 1 would be enough if I wanted to be in k. Once it's not 0, then there is something non-zero there. When it's 1, only k is there, only constants, and when it's 2 and higher, you can find functions there, like non-constant functions.
Riemann's theorem is much stronger than this. Gives you the
Right. Oh yeah.
This is like you choose just the simplest case and you got this.
Right. Yeah. But I mean, I couldn't have done this without Riemann's theorem. Okay, so this means what we wanted, because this means that the pole divisor, and here, by the way, there is no other function field, but I just wanted to get us used to this notation. is k times p for some k between 0 and n. I mean, what do we know? X satisfies that. So the only poles that are allowed to X to have is at P. And I'm not saying it has n poles at P. I don't know. I mean, maybe it's not with equality, like, you know. Maybe I'm allowed to have 5 poles and I only have 3 poles. Could be, right? So what I'm just saying is that the only prime divisor that participates in the pole divisor of X is, you know, there are only P with multiplicity, which is not larger than n. But it could be 0 technically, it's not, but it could technically be 0 for a second. But I promised you it's at least 1, and you will need that at least 1 in a second. That at least 1 will be very important for us. So that will make sure that there is at least 1 place above your place. So I want this one really. It's an important one. But why can't k be 0? Exactly. And that's maybe why we chose the letter, I don't know. But if k is 0, it means that X has no poles. Because it has no poles other than in P. And if k is 0, it also has no poles in P. And so it's constant. So it's in K, capital K. And it's not in K. Because we made sure the dimension will be large enough so we can choose X, not in K. Yeah, so that's the proof. It's a very important lemma. It's like telling you want to understand something geometric, look at the corresponding function that kind of encodes that point. Okay, so after the break, we are almost in a position to prove the fundamental equality. Okay, we'll see. Let's take a break. Right, so now we're ready to say, using that innocent looking lemma, that if you look at a prime divisor at the lower function field, then above it there will be a prime divisor, not like ending, and only finitely many. Okay, so let f over L be a function field extension of E over K, and P, a prime divisor of E, or E over K, then the set of prime divisors of f over L lying over P is finite and non-empty. Right, so you have E over K, f over L, and you are looking at a place at the bottom now. That's the right direction to do things. And then you're asking who is above me, and I know that if I would have started something in the place above, then there is something below it. But technically, it could be the case that if something here, there's nothing above it. But there is no such a case. So this lemma tells you that there is at least one prime divisor lying above it, namely that when you restrict the place of P to E, you'll get little p and so forth, and only finitely many. At least one, could be one, but only finitely many. Okay. Good. So let's prove that. And it's really important that we are not talking about like the rational function field and then some place above it. We're looking at any function fields, right? Any two function fields. So that will enable us, like we already making sure that our mechanism will enable us to do like what's called towers. So function field extension over, you take the rational function field, you extend it, and then you extend that, and then you extend that. You want this kind of general result that tells you no matter how the base field function field is complicated, still this is true. This is something that we really want to have. And so let's do the proof. So again, we want to understand this prime divisor. So let's take an x that is guaranteed from the previous lemma and work with that x. So by lemma 7, that's what I just erased actually. By lemma 7, there exists an x, which is E and not in K, if you remember, such that in a sense, its pole divisor, but in E, because as an element in E is K times P for your P, and K is at least 1. Right, that was a kind of a little bit tricky to make sure K is at least 1. So actually maybe I'll ask you. So now if you want to figure out what are so these are kind of abstract things, we don't understand them. But we do understand, and this is also abstract, by the way, right? But we do have X that kind of explains this P. And its pole divisor is P. So what should be like what are these in terms of X? Like what they should, there's only one thing that could possibly go right. So how can you relate X to these? Or some divisor of X to these? And X is also an element in F. Right, so. Okay, so I'll tell you. So let's look at this. Right, so let's look at X element in F. It's an element. It has poles, like potentially it has poles because it's not going to be in L. So if there is any hope to finding pole divisors, like the prime divisors above little p, they are going to be the pole divisor of X. So I don't know what it is. I'm going to write it like, I know it's a divisor because we proved every function has finitely many poles. So I know it's like a divisor, not a pseudo divisor or something like that, which we don't talk about anymore because we don't need to. So we have this. And what I'm claiming is that these PIs are exactly the PIs that I'm looking for. Well, sorry, I started to write without no words. So consider this. So we consider this divisor, write it kind of, in terms of the prime divisors that appear there. Exactly. It's fine just because the divisor. Right, these are integers, these are prime divisors in F, which I don't understand yet, but I know there are some prime divisors in F, and there are these poles. So first of all, note that it's not an empty sum, right? Because if R is 0, if there is no poles to X, it means that it's constant in F over L. So it's in L, because F over L is a function field, right? So forget about the fact that X was coming from here and so forth. It's a function field. If you have an element in F which has no poles, it's in L. But it's also in E, because we started with X in E. So what does it mean? It's in K. Right. But it's not in K, because we made sure, here it is, to choose something to suggest not to be in K. That's what I really needed that. I don't want to look at constants. I need functions. Good. It's in E and in L. And if you remember, the intersection of them is K. And when you right, yeah, it's kind of new. But when we do function field extensions, we have this E is in F, K is in L, and this by definition of function extension. So what I want to show, of course, is that those PIs are precisely the prime divisors above it. So let's show that P1 up to PR, now I know R is not empty, like there's something here, are precisely, like these are all and no other, precisely the prime divisors of F lying over P. And remember, lying over means that when you restrict it, you get P. Like when you restrict a place, you get the place corresponding to P. Or when you restrict evaluation, you get evaluation that's a multiple of the evaluation corresponding to P, and so forth. Like it's equivalent to that. So we have two directions to do. In one direction, so if you take any P that lies over P, so you write it like that. If you take any P that lies over P, I want to show it's one of those PIs. So take any P lies over P, then, so we know that V little p of X is negative, right? Because P is a pole of X. K was at least 1, so it's really a pole. It's like the valuation is like minus k. So it's negative. And so what can you say about VP of V capital or V calligraphic or whatever, P of x? So how does this relate to that? Exactly. So you look at the verification index, which is a non-negative number, so just 1, because that's like the extension of groups in somewhere. So that's positive, that's negative, so that's negative. Right, so this means that P is one of the PIs. Because the PIs are precisely those prime divisors of F such that VP of X is negative. Like these are the poles. Right, because P1 up to P are precisely those places such as VP of them is of X is non-zero, is negative. In the other direction, I don't know, it looks like a, in the other direction, right, so it's kind of almost the same, easier maybe. So right, so what I want to say, which is true except for something, I want to say, okay, let me write it correctly and not what I want to say, and then fix it because it's harder than just to say it. So by claim 5, and since I'll remind you what it is, and since F over E is algebraic, it's even finite. Claim 5 told you that below every place there is a place, assuming that this is algebraic or finite. Right? Technically, when you restrict a place to E, it could be trivial on E, but not in the case where this is algebraic or finite. And because this is algebraic, we know that for every I, so we fix I, one of these PIs, so we know that there exists some place Q, prime divisor, let's call it, instead of a place of E over K under PI. Right, so what I'm saying now I'm saying take one of those PIs. Look at the prime divisors that below it, and there is something that's below it because F over E is algebraic. And that's Q. Let's call it Q. I mean, I know that I want to show that Q is P, right? But I'm kind of, that's the next step. I know that there is some prime divisor below it, and therefore, again, VQ of X for that mysterious Q is let's write it like that. Right, so usually you write it here, but V little q of X and V pi of X satisfies this relation. This is not zero, it's at least one of the time. And we know that this is negative. I mean, this is positive, this is negative because pi is a pole of X. So this is negative. So this means that Q is a pole of X. So Q is a pole of X. Hence Q is P. Because the only poles of X in E are P. Right, so these are precisely all the prime divisor that lies over little p. Now we can forget about X. And X was a tool for us to prove that. Above little p, you have finitely many, but non-empty number of, non-zero number of prime divisors. Yeah, but that's a prime divisor. Right, so prime divisors are just like, so a divisor was a sum of these prime divisors, but I'm talking about prime divisors. So no, because 2Q is not a prime divisor. Prime divisor was like, equivalence relation of places or something that's abstractly defined. And when we define divisors to be like a formal sum of those. Yeah, right. Yeah, good. Can I erase this? I mean, now I want to state kind of the most important theorem of the day for some time now. And it's called the fundamental equality. So, it's fundamental, so it must be important, and it is. And it actually tells you much more information about, if you look at a prime and the primes above it, what can you say about how many are there and what's the E and F's. So let's see. So let's say F over L. Here is a finite, not just algebraic, extension of E over K. And let little p be a prime divisor of E over K. So again, you look at the prime divisor below. And so what I'm saying is that so it's fundamental equality. So there's an equality. That's already a good start. Good. So if you take a prime divisor, any prime divisor at the bottom of E over K, and you look at the prime divisors above it, so you write it like that, all the prime divisors above P. But let's denote it in this picture by P1 to PR. Each of them has its own E and F, which we still don't quite understand what they are, but these are important numbers for us, you will see. But I'm saying that there is some invariance going on here. So if you sum over all the prime divisors above me and take the product of the E's and the F's, you get always the field extension, like the function field extension, not L over K, the field extension. That's kind of fantastic, right? I mean, so right, yeah, you'll see much more than that, but that's a very strong statement, much stronger than there are finitely many places above you or something like that. I mean, you need that for the proof, but good. So let's prove this. Right, so F, remember, is like the residue field extension. So you look at OP over MP, so that's the residue field of this prime divisor, and it extends this residue field, and the index is F.
So how large was it?
Right, the residue field, how did it increase, to what extent? And this was like the valuation. You look at but here you look at the valuation, look at the index of the valuation, the image of the valuation, how bigger is this subgroup compared to that? And we'll talk about exactly what it means in a second. Not in a second, but you'll see in examples, and then we'll talk about it more. And we'll see the examples today. So this kind of talks about like, okay, I don't know exactly how to, kind of root multiplicity in a sense. And this is a phenomena, this is an arithmetic phenomena. When you study algebraic geometry, if the K was algebraically closed, this is always 1. But in our case, this is kind of the arithmetic. The fact that we're over 5 require us to keep count and ask, what in this statement, in the sum and so forth, what are the residue fields? So I'm working over F5, but some of my roots are going to be in F25. So this kind of keeps the right count for that. And the fact that kind of geometry and algebra kind of behaves like that, it's really cool. So you'll see, I mean, today we are going to see, like, right after proving this theorem, we're going to see examples, like one example, but very, very long. And then next time we're going to see more of that example. You'll see what I'm talking about.
That part is like 7z over z, and the right part is like
this, yeah.
Yeah, so
exactly.
This is like 7z over z, and this
Right.
is like
S25 and F5.
yeah.
Right.
And this is like 7 to the right thing is like the and the left thing is like the other. So how do I think about it?
Right, the ramification, yeah. So it's called the ramification. You will see what it is in the examples. Like you'll see in examples, what does it mean? Like how does it look in the example? And I think it's very useful. Usually I do the example at the end, but I felt like, I should. Oh. Okay, but let's move this and then we'll, actually the examples we'll do on the slides because there are many pictures that I do. So I think it's better. But let's do the proof. The proof is really easy now. We just like playing, like take everything we did and do it, but you need to do it. So let denote by, so I fixed little p, and let denote by p1 up to pr. We know it's a finite number. The prime divisors lying over little p. Okay, so actually I'm going to need not just the lemma that we proved, but actually a line from it. So, but it was a second ago. So by the proof, not by lemma, by the proof of lemma 8, this means like, bad design on my part, really, right? But there exists an x. You say I need this x still. I mean, still need it. There exists an x which is E and not in K, such that the pole divisor of x as an element in E is K times P. K is at least 1. But the pole divisor of x as an element of F, it's exactly those MIPIs. And that's how we prove this. There are finitely many but non-empty number of points above us. Right. No, the betas were we proved that the betas were the places. In the lemma we proved that all the prime divisors that I sum over here, right, that are. No, it is a lead beta. No, yeah, I did say. So, right, but these are the prime divisors that lie above little p, and by the proof, and the correctness of the previous lemma, we know that the betas come exactly as these elements in the pole divisors of x as an element in F.
The line of opinion is that they are the same.
That's what we proved. We proved that. We started with an x. That's a good point. We started with an x. We started with a p. We got an x. We thought of it as an element in F, and said it's a divisor. So you can write it like that. But then we proved that actually these beta i's that appear in these pole divisors, and only them are the prime divisor that lies over little p. And I'm using the proof and the correctness, like at the same time, like yeah. So maybe I had to separate. It's not me even. I didn't develop this theory, right? Okay, so I slightly kind of made it a little bit more approachable, at least for me. But okay, but yeah, that's how they do it. Good. Okay, so we know that. And again, we want to prove these things. These are numbers. We don't understand them. Each of them lies in a different world, measure different things. But we understand x, so we are going to work with x. That's the general philosophy. So what do we know? So we know, if you remember, if you remember, let's look at the degree of this divisor, of the pole divisor of x as an element in F. So on one hand, it's just the degree of this divisor. So it's just, these MIs. I know what MI is, by the way, right? It's like the value. It's not a weird number. It's the valuation according to pi of x, or maybe minus that, because that's what appears in the pole divisor. Like, it's a non-negative number. It's a positive number, but its minus is how many the valuation of x. But anyhow, I don't need that for a moment. The degree of this thing, just it goes through the sum, through the MIs, and goes to the degree of the PIs. Right? On the other hand, do you remember in terms of field extensions, what is this? Like, fill the blanks. Yeah, we did it with 0, but right, but it's yeah, good. So this thing, we did it for the 0 maybe, but so if you remember, we proved that, we proved that the number of zeros in poles of X is exactly this extension, degree extension. That's how we kind of get as a corollary that the principal divisor of an element has degree 0, because it has the same number of zeros in poles. And all right. So we know these two. So you see, I really work with X, not just with the numbers. Now MIs, let's look at the MIs for a second. So we know what MI is, right? As I said, it's, well, maybe the minus of the valuation of pi at X. Oh, someone really. My wife sent me a picture of my daughter, so I'll see it later. So MI is minus the VPI valuation of X, right? Because what is MI here? It's the valuation, it's a pole divisor, so it's minus the valuation of pi at X. And I really want to find it to show the, to kind of have the E appearing, because I want, you know, some EF equals something. So how can I get an E out of that? Oh, it's a kind of silly question, but right, I mean, this is it's this thing, because X is an element in E, so I can, and PIs are above P, so I can do that. And this is what? Exactly, minus K, right? Because how many poles or zeros, but we know it's a pole, X has at P, well, K, right? Or like minus K multiplicity. So the minus actually get canceled. So, so what we get, if I plug it, the MI here, so I still have the F over Lx, and that equals to this sum. Now I'm going to replace the MI by minus K times minus this thing. So it's, ignore the minuses. K times that. So I want to write K times that times the degree of Pi. But K is independent of I, so I can put it outside. I can put it outside. And then I can have this modification index multiplied by the degree of Pi from here. Okay, it starts to look good. You know, you have like E's, but you don't have F's. You have this weird K. You also don't have here what you want really. Okay, so it's a mess, but at least you have a sum of E's. And now let's try to make a, oh, okay, so no, I did it in the other direction, so okay, so let's continue on. So now, let's look at this thing for a second. I mean, I want to look at F over E, really, but let's start with this for a second. So F over Kx, you can write it like, you can split it in the middle by using Lx, because L is a superfield of K. Right, if you remember. And that, remember this lemma that told you that when you have X transcendental over K and L, when that's the same as L choose K, I like to call it. Okay. So this means that F over Kx is F of Lx times that. F of Lx is this sum. So I'm going to write this sum, and I'm going to take it to multiply it by that, but I want to put that term next to the degree. Okay, so it's the sum. So there is a K, sorry. When there is a sum, the E's are there, and then you have the degrees, but I want to multiply the degrees by L choose K times the degree of Pi. Okay? Maybe I'll erase this part. Are we good so far? Just doing the calculation in the right way. But I mean, any way that you, any greedy way that you lead to E's and F's will work, but that's one way. Now, the point is that if you remember, you had this K, L, FP, EP. just remind you something, a formula that we wrote. So this is the degree of little p. This is the degree of capital P. This is L over K. And this is, we define it to be f of p over p, right? Which we want to see them. And what we have there is Lk times deg pi. So what we have there is this. So you can put an I if you want. But it's equal to that. Everything's finite. So, the left-hand side, so it's k times the sum I goes from 1 to r. You have the e's, which is good. And then you have Lk times deg pi. So it's deg p, which is independent of the sum. Right? Deg p times fpi over p. Right? Good, and the deg p can go outside. Right, so that's k deg p times what we wanted to see. Now we're almost done, because, I mean, we don't want to see that, but we also don't want to see that. And this is the same amount that we don't want to see. So like f over e, which is what when you want to see the index of f over e, this thing, let's split it as kind of we usually do at k of x. That doesn't make sense? Yeah. It's not the usual direction, so it's confusing. Right, so f over e times e over kx, it's f over kx. So when you divide, it's psychologically hard to do. So f over e is that over e over kx. Time what you want, and the sum. Let me just write EIFI because I'm lazy. And I really don't want to see this. If this would be 1, I'm happy. And this is 1. Why? Because exactly. So it's a little bit of juggling. Other than that, it's everything that we did. So we know that the degree of the pole divisor of x is always e over kx. And in our case, it's k times deg p. Because the pole divisor is just k times p. So these two numbers are the same. So this is 1, and we are done. Right? Yay. We proved the fundamental equality. Questions?
The physical is because.
That's always true. That's a theorem that we proved. Right. And we used it before, by the way. Yeah. And the right one is because we know that in our specific case, x infinity is just k times p. So degrees is k times degree of p. K is larger than 1 if you're, or if not.
Smaller.
No, it's equality.
It's equality.
Yeah.
You chose the case to be equal.
Right. Right. It was an n, and then k was the right. Exactly. There's a picture that we'll see. Like intuition is hard for me. I mean, there is an intuition, but yeah, it really has to do with the fact. I mean, we're going to see examples now, and maybe that will be better. But yeah. So I don't know. So I want to do. I don't want to do it because I'm going to be inaccurate. But generally you have this curve, and what this theorem tells you that a line, so this is like fixing x to be something. So like in the rational function field, points, like if things were infinite, like if the field were complex numbers or something, when for every alpha, this is a prime divisor, and these are only the all prime divisors that you have, except for infinity. And what this tells you that if you're looking above this place, the places that you see, always the number of them is always the same if you count correctly multiplicities. So for example, here it seems like you have only one point of intersection, if we manage to get it, but actually E is 2 because you touch it twice. That's what kind of more or less.
So what is the intention about points lying on points?
Yeah, that's what I'm not doing. You're right. And by the way, this you can look at this. You can say, well, what's going on with that? Well, that's not fair. That's a singular point. You shouldn't look at this curve. You should look at another curve that has the same function field. So I mean, there is like an entire course. I need to kind of really explain this relation. And I can. I sent links if you want to look at it.
How do you think? Just maybe how do you think about points lying over points in this sense? Or maybe if you can.
So let's do the example and you see how I think, because that's how I think about it. I mean, you can do that. And by the way, the Fs means that sometimes, it's not algebraically closed. So when you do this line, so first of all, there are prime divisors that don't correspond even to field elements. But when you do this line thing, you may not see anything. There are no solutions. Like setting x equals to 4, there are no solutions in terms of y, but there are solutions in field extension. And the F tells you that every solution that you see, you should multiply. It's going to be a irreducible polynomial that divides kind of your polynomial, then you should multiply it by the degree of that polynomial. Like it doesn't do justice. I can't really explain it without doing much more work. But nonetheless, I think that the examples that we see are good. I mean, it's maybe you can argue about that, but I don't think you have to have the geometric intuition to understand what's going on. Because in a sense, it's also misleading. So we're going to just develop our intuition. It's not mine, it's like the people who does that intuition. And as I said, there are many drawings, and the math is like, there is no math, I'm doing examples. So it's very easy to follow. So I think slides are better for this part. I mean, math, you need both. But just doing like some simple manipulations, I think you'll be fine. And we're going to start today and continue next time, but there is no next time, because there is the Weizmann Winter School. I mean, there is next time. So the world is ending. But there is the Weizmann Winter School, and you should come, of course, I told you. So I'm going to record, I actually started to record some of these parts and other parts as well. Some of them you don't, I'm not expecting you to see. It's all very simple and you're understanding there. But let's start the example still here, and we'll meet in 2 weeks from next week. But you should come to the Weizmann Winter School, by the way. So you see everything is here, all we did. You see, when you do it like that, like so quick, you just, yeah. Okay, so that's the proof that we saw. And I want to give you the example, and what other example than our example, right?